Hello, everyone. This is Yuexie from the School of Computer Science in the University of Adelaide. Today, I will introduce the project Blending Strategy Optimization, which supervised by Professor Frank Neumann and Dr. Anita Neumann. Our business partners is Aussie Mineral. This project is under the Program A in Research Group 3, Optimization Group in the University of Adelaide. The objective of this project is to maximize volume of valuable metal, for example, like gold, copper, silver, and others. Here is the outline of today's presentations. First, I will introduce three main outcomes of this project, and then I will introduce the background and some significance of this project. Then I will introduce the research progress about how we achieve those three outcomes. In the end, I will introduce one important methods and the result of this project. First, there are three key findings of this project. We first developed a mathematical model that optimized the blending strategy and named the problem as stockpile blending problem. And based on this initial problem, we considered the large-scale problem and the proposed heuristic approach that outperforms original approach. Then, also based on initial problems, we considered the stockpile blending problem in a stochastic environment. Then, for the first problem, then I will introduce the background of this project. The stockpile blending problem is an important component in mining engineering. The result of stockpile blending problems can reach hundreds of millions of dollars. And here is the upstream of the supply chain in mining engineering. We first mine material from open pit mine or underground mine, then shipping them from mine part to run off mine stockpiles and store all the material in the stockpiles. In our project, we concentrate on generating each bench which claim material from stockpiles and sending those bench to mill part. After some chemical processing, we obtain our final production, which should match the market plan or the customer requirement. So in this project, the strategy to generating this bench is constrained by the mine plan because it decides the available resource in the stockpiles. And the strategy of generating the bench is also constrained by the mill side because it limited some parameters of those bench. And in the end, the strategy is also constrained by the market plan. And we consider the problem with a large scale is more realistic because if we have to propose the blending strategy once a month, it will waste too much time. So we can gain some benefit if we can propose the blending strategies for those bench for up to 1 year. Up to 1 year, yeah. And the uncertainty in the geological input data also affects optimizations. So we consider the problem under uncertainty input parameters. First, as an initial problem, we express the stockpile blending problem as an optimization problem with mathematical model and propose heuristical algorithms for the problems. In the beginning, 3 years ago, when I first started this project, what we have is a really large size spreadsheet proved by Aussie Mineral, and it contains different parameters, contain different calculation processing. So what we did, we first analyzed the spreadsheet to select some key parameters and key calculation functions, and we express these whole problems as a nonlinear model. Then we translate mine and mu models into a computer language. Here we use Java. As we know, as I introduced before, these problems, even we only have one objective functions, it's still complexity because it contains 3 different types of constraints. So we introduced 2 repair operators to tackle 2 complexity constraints in the problems. And after that, we investigate the performance of a classical differential algorithms. For the second finding, we consider the problem with large scale, and we hope can plan parcels of benches for up to 1 year. And the progress involved identify parameters which directly affect the objective value. Then we propose a method to maintain the parameter constantly, and we implement the model in Java code and apply a heuristic approach in solving the large-scale stockpile blending problem. For the third key finding, we consider the stockpile blending problem with uncertainty in material grade and apply chance constraints optimization. We first reformulate the model by assuming material grades as stochastic parameters. Then we apply chance constraint optimization, which I will introduce later, and propose surrogate functions of those constraints. In the end, we applied the algorithms to solve the problems. Now I will introduce what is the chance constraint optimizations, because we already developed a nonlinear continuous optimization model to integrate uncertainty variables to optimizations. And here we introduce these chance constraint optimizations to guarantee the constraints is violated with a small probability to tackle the stochastic material grade. Here, this is the general formulations of an optimization problem under uncertainty, which object to minimize or maximize the objective function and subject to an inequality constraints. After we formulate the constraints, we obtain our chance constraints. Here, alpha is a given probability level, can be given by our business partner of the mineral. So now, back to the stockpile blending problem. We assume material grades of stockpiles and overall hoard are stochastic variables with expectation and variance. So the resulting decision ensures the probability of complying with constraints. Here, this probability is the confidence of being feasible. These 3 inequality constraints is given by the initial problems. Then we define these 3 confidence of being feasible, these 3 probabilities, and reformulate these 3 inequality constraints to the chance constraints. In the end, I will show the results of 2 types of stockpile blending problems. First, the numbers list in this table shows the result of 1 month stockpile blending problem, which is our initial problems. And we take the first instance as an example. We find in this instance, it only contains 2 parcels, or we can call it benches. And each bench can claim material from 6 different stockpiles, which means the length of decision variable of this instance is 12. And we find, and the result listed in the ORG column means the result we directly copy from the spreadsheet proved by all the mineral. And we find the result obtained by DE-based algorithms is better than the original result. Then this table lists the result for some large-scale stockpile blending problems. We take the first one as an example. It contains 5 months. And it contains 5 months and 11 parcels. The length of the decision variables of this instance is 76. It's really a large scales. And then we also can find that the result obtained by DE algorithms is better than the original result. And according to the conclusions, we finding from these two tables, we find the result obtained by applying the algorithms is better than the original result. So for future work, because as I introduced in the help presentations, for 3 different types of stochastic blending problems, we only investigate the performance of classical DE algorithms, which is a good, well-known evolution algorithm, but a little bit old. So maybe in the future work, we hope to improve our optimization tool and leading to the improvement of objective value. That's it. And in the end, I want to take this chance to acknowledge my supervisors, Professor Frank Neumann, Dr. Anita Neumann, and our business partner, Ozy Mineral, and also our research consortiums who support my PhD degree for 3 years. Thank you very much.